So I hope everyone is enjoying this year's GopherCon. So I will introduce myself. So I am Jubi and I work with Key Value as a tech lead. So we are a product development hub based out of Kochi, Kerala. So we work with different startups and scale-ups across the globe. So I have been dealing with, involved with building 0 to 1 products for seed-funded startups to building and leading teams for super high growth series funded startups. So that is about me. And this is what ChatGPT thinks about me. Mostly correct, but not complete. So, yeah. So, a bit of a spoiler alert. I'm sure that you won't be expecting to master concurrency in a 20-minute talk. But the idea is to leave out enough pointers out there so that I could set a path to generate enough curiosity to learn and master concurrency. So that is the idea of this talk. So, yeah. So we'll be mostly going through certain patterns in Golang. So like worker pull patterns, pipelines, and fan out and fan in. So we'll actually see how some of these patterns are implemented in some of the products that I have worked with in production, and also we'll see how some of these patterns are implemented in some of the open source projects as well. So this will be the structure for the talk. So before diving into the patterns, let's see how the concurrency model for Go came into picture. Okay. So in 1978, Tony Hoare actually published a paper called Communicating Sequential Process, now mostly called as CSP. So the core idea of it was it made communication the foundation of concurrent programming. Meaning if you want to communicate with like two processes, you should always communicate via a fixed defined channel. You should not share memory. So that was one of the core ideas that was mentioned in that paper. So this is okay, there were actually many languages born out of this paper as well. And this is also the foundation of Go's concurrency model. Go actually adopted the ideas of ideas from CSP and also made one crucial innovation, which is they introduced channels and they made channels as first class values. So we'll see what I mean by first class values in the later part of the talk. So now let's dive into patterns. So first we will deal with worker pull. So every pattern actually tries to solve certain problems. So what is the problem that the worker pull is trying to solve? It actually allows us to reuse threads for multiple tasks. So let's say we are actually, let's say we are actually dealing with multiple OS threads, right? So we know there is an overhead in creating an OS thread, right? So worker pull actually allows us to override that by creating a fixed set of threads, and we can push tasks to that. So that is the benefit of worker pull pattern in general, or we can call it as thread pull pattern. But does that benefit really apply in Go? Because in Go, we know that we are actually not dealing with OS threads, we are actually dealing with Go routines, right? So let's see. So that benefit doesn't apply in Go. So what is the benefit that is for worker pull in Go, right? Go routines are actually later multiplexed on OS threads, so that is why that benefit doesn't apply in Go. So what is the benefit? The benefit is to limit the amount of concurrent work in flight. So we want to restrict the resource usage for that, for a program, right? Be it memory, be it network, whatever. So we want to limit that and restrict it. So for that, we could actually use this worker pull pattern. So let's see a simple worker pull pattern in action. So here, you could actually see this is a very simple worker pull pattern where we spin up a set of Go routines, and each of the Go routines are reading from a single channel. So this is like, we spin up Go routines up to a certain limit, and we will actually read from a channel, as you can see here. And then we will pass on work to that channel. So we have like spawned up like few Go routines, and it will be read from a single worker pull, single channel. So this is a simple worker pull pattern, but there is an issue here. So what is the issue? It leaves workers forever. So we do not have the ability to track the workers here, right? And also the workers are not getting shut down. So let's say if one of the Go routines has processed executing its task, and what is the issue when we actually leave it like this? So let's say one of the Go routines might be referring to some of the variables which have a heap reference. Since the Go routines are idle right now, that won't be garbage collected. So we cannot leave this Go routines as such. So we want to clean these Go routines up once all the tasks are finished. So let's see, how do we fix this? So this is the current simple worker pull implementation that we have. And how do we fix this? We introduce wait groups. I'm I think you are aware about this wait groups in Go. So we introduced wait groups to actually track the Go routines, and finally we actually close that channel. So the channel that we are actually sending the data to, we actually finally close it so that all the Go routines will exit out of Go routines will get exit once all the task that has been passed to the channel is completely processed. So this is how we could actually track the flow of Go routines, and we could actually close the channel, and all the Go routines are now exited from the program. But here there is still one more issue. What is it? So here there is a chance of idle workers, especially towards the end of the work. Even if we are cleaning up the Go routines, let's say here you can see G3 and G4 has finished executing its task, and it is actually waiting for the channel to be closed so that it can exit. And during that time, G1 and G2 is still in processing. So what is the issue with leaving these idle workers for a long time? If it's like few workers, it might not be an issue. But if let's say if we have like hundreds of thousands of Go routines out there, we know Go routines are cheap, like 2 KB stack size. But if we have like thousands of workers running, that may not be cheap. So it might consume certain resources, right, which we cannot ignore. So that is one issue. So ideally what we want to do is let the Go routine process it and then immediately exit without waiting for any other dependencies to be processed. And also there is one another issue. Let's say G1 is actually currently processing state and it causes an accidental deadlock, right? Now if there are like thousands of Go routine running and you want to debug it in production. So let's say you have profiling enabled in production and you are getting the Go routine dump out of it. And that Go routine dump might look something like this. This is just the first few pages of that Go routine dump. Like if you have like thousands of workers running, then it'll be pretty difficult to pinpoint, right? So there are like a couple of issues with leaving the workers idle So we want to get the same benefit. What is the benefit? Which is to run concurrent, limit the amount of concurrent work in flight. And at the same time, we don't want any idle workers as well. So how do we do that? So here, you can see earlier we have a single channel to which all the values were actually passed, right? And we have a fixed number of Go routines waiting to read from that channel. But right now we are creating a new Go routine for each of the tasks. We know that, there is no overhead in creating Go routines, right? Because actually we are not actually using the OS threads. So we actually create a new Go routine for each task. So once that task is done, that Go routine is done and finished. So we'll spin up a new Go routine. So here, what is the issue now? So we are actually spinning up a new Go routine for each of the tasks. So let's say if there are like 1,000 tasks in there, so we'll spin up 1,000 Go routines. Now we want to limit that, right? Earlier we were limiting it, but there were idle workers. But right now we want to actually limit it. So how do we limit it? In this pattern. We use a semaphore channel. So for that we are actually making use of a buffer channel in here. So we introduce a buffer channel with a certain limit. And so the idea of this is a buffer channel. So this will be a non-blocking operation up to the limit. So we can actually keep pushing values to this particular channel. And it will be like this send operation will only be blocked once the buffer is full, right? So once the buffer is full, no more Go routines can be created because it is blocked there. So in this, and when is the value from the buffer released? It is released after each of the function is, we are receiving values from the semaphore after each of the function is exited, right? So this way, doing this pattern, we could actually limit the number of workers running, and we could also immediately exit out of that loop as well. So this is how we could actually solve that problem. So here we have solved the problem of idle workers as well as we have solved the problem of concurrent amount of concurrent work that is happening at a time. So this is what we have done right now. The first one is a workable pattern where we have a task which is actually sent to a channel, and there are like Go routines waiting and reading from that particular channel. So we are executing it, and that has an issue of idle workers. We could actually fix it using semaphore pattern. We introduced a semaphore channel. We are limiting it. We are spinning up new Go routines for each task, and we are actually limiting it using this buffer channel. So which one to use? It depends on your context and what you're trying to achieve and the trade-offs that you want to make. Now let's see a different pattern in action. We will actually see how we have used this workers in production for one of the use cases. So the use case was this: we used Kafka for PubSub. So we want to conceive messages from it, and we need to concurrently process the messages. So we use this workable pattern where we could actually send the message to the channel, and there will be like multiple workers listening and processing that messages. So this force select is the usual is a pattern that we're commonly used to continuously receive or iterate receive message from a channel. So we receive the message from the channel, we read the message from the Kafka, and we actually put it onto the channel, right? So, and there will be like workers listening, and it will be actually processing those messages. So now let's see something different. So here we are actually handling something like using context, right? Let's say your instance is getting shut down. You want to gracefully exit out of the instance, right? So there will be like certain workers processing, and we want to wait for those workers to finish processing, and at the same time, we don't want new tasks to be sent to the channel. So how do we gracefully exit out of that loop? So whenever we receive an interrupt signal from the OS, when your container or whatever you're running in is getting shut down, we are handling it using context, and we have the context, and then after that what we do is we actually immediately close the channel. So no new messages are sent to that channel, and then we use wait groups to wait for the existing routines to finish, so we could gracefully exit out of the system. So this is one such pattern that we actually used in production. So yeah, now let's see a different pattern, pipelines. So these pipelines, so this pattern that you could actually use when you have your data flowing through different stages. Let's say you have an input stage, then followed by a validation, then followed by pre-processing. So your data needs to flow through a plethora of stages. So in that scenario, you could actually use this pattern. And in Golang, this series of stages are actually connected via channels. So let's see an example of that. Okay. Let's see you want to process an image. So you uploaded an image, then after that you want to resize it, then you want to add watermark, or like your process should, your input should flow through different stages. So let's see how it has been handled. So here, in the first stage, we receive a list of images. So there will be like thousands of images coming in. So for each stage, we will have a Go routine running. So that Go routine will be listening to the input. And once that stage is completely processed, what happens is we'll push the output to a different channel. And that channel will be the input to the next stage. Likewise. So the output channel of the upload image will be the input to the next stage. And the next stage, similarly, the next stage will be having a Go routine running and listening to that channel, and the output will be passed on to the next channel. So that is so it will be your input is actually flown through different stages, and finally you get your processed output image. So here, when you just simply look at it, it might not sound like a concurrent operation, but if you have like thousands of images coming in, the thing is, it ensures that each image is actually processed sequentially through the defined order. At the same time, you could actually concurrently process the different images, because actually we are actually pushing the images to the channel, and then later the Go routines are actually picking it up and processing it. So let's take a look at the pseudocode. So this is how it might look like. So we upload the images, we pass in the images, let's say, and to the next stage we are actually passing the output channel of the previous stage. And so here you have the upload images, and as I said earlier, each stage will be having its own Go routine, which is actually listening to the input. So here it is actually listening to the input and actually writing the output back to a different channel, the output channel. And that output channel will be the input to this next stage, which is resize images. And that stage also have a Go routine, which is actually listening to that particular channel. So it is each stage is actually connected via channels. So, and finally, the images is, the output of all the images is fed to a final output channel, which is read from your main function, as you can see here. So here there is a caveat. Let's say we did not close this channel, the one that I am highlighting right now. What happens? If you do not close that channel, not for this particular stage, but for any stage. Let's say if we do not close the channel, what happens? It will result in a deadlock. Why? So here, as you can see, I will highlight it now. So this one. So you are actually waiting for reading the messages from this particular channel, right? So you are actually reading the messages from a channel, and if you have not closed that channel, it will, the read part will be like waiting forever, which results in a deadlock. So it is important to close out the channels for each stage once you're done processing with it. So this is about the pipeline pattern. Now let's see a different pattern in action. Sorry. Yeah, sorry, this is not working. Yeah. So yeah, now let's see a different pattern in action, which is fan out and fan in. Fan out is something like, it might sound similar like a workable pattern where we fan out the processes. So we'll be like fanning out to different go routines, and each go routine will be writing to its own channel. The fan out and fan in mostly works together. So once we have fanned out the results, we actually need to aggregate the results from all the fanned out workers. So we'll be aggregating it using a fanning pattern. So we'll just see an example of it. Let's take the example of this. Let's say you're working on an e-commerce product. You have like multiple microservices like order service, inventory service, payment service, and shipping service, and you want to aggregate the logs from all the microservices, right? So what you actually do is you have a service which actually aggregates the logs from all the services and finally writes the output onto a object storage or S3, something like that. So you will be receiving log events from each of the services one by one. Then what we'll be doing is we'll actually be processing it. So what this processing, the distributed log processor would do is, let's say you want to filter out certain logs, or you want to add metadata or enrich the existing log. So that is what this log processor is doing. So for each of the event received, we'll spin up a go routine, and the processing happens inside that go routine. And after the processing, we actually write it to, so each of the processes, as you can see, each event like 1, 2, 3, 4 is received, and after that, each of the go routine writes the result back to its own channel. As you can see, go routine 1 writes to the first channel, followed by go routine 2 writes to the second channel, and so on. And finally, we have the fan in part, where we have individual go routines listening to each of that output channel, receiving the values and aggregating it and writing to a single channel. So thus we could actually concurrently process all the messages that has been received, and then finally output the received output to the single channel. So, and finally we could actually write it back to the object storage or S3 or whatever you are using, or whatever you want to do with that. So let's take a look at the pseudocode for that. So we receive the image. So this is where, let's say this is the log stream in which we are actually receiving the event one by one from each of the services. And we receive the event, and after that, as you can see, we create a go routine for each of the received event. As explained earlier, we create a go routine and there is a channel associated with it. And finally, the result of that go routine is actually pushed onto that channel. And at the same time, there is a go routine which is actually listening onto the channel, which is to fan in the results from that particular channel, and then finally write the result back to the result channel. So here we have the result channel to which finally we aggregate the result, and we have the final data in here. So thus we could actually guarantee the concurrent or parallel processing of the received events. We process it and finally write it to. Now let's introduce one nuance here, which is, let's say we want to guarantee ordering. Like we will receive the log event one from one service first, and followed by the other one. So the log events will be received in a particular order. So we want to guarantee that we want to actually write the final message to your S3 or object storage in the same order that we receive the log events from, right? So how do we guarantee ordering? In this pattern, the ordering is not guaranteed. Why? We have like different go routines processing. We don't know which go routine will be processed, finished, will execute first, and we'll place the result back onto the result channel, right? Any of the go routines can actually process and put the result back onto the result channel, right? So here ordering is not actually guaranteed. So how can we actually guarantee ordering in this pattern? Let's see. So here the approach is similar. For each received event, we actually create a new go routine. So here is the Go routine received. Here is for each event we create a new Go routine and it writes its own channel. The only difference is that after writing to the channel, before writing the result to the channel, that channel is actually placed on a different channel. Here you can see there is a processing queue channel. It is actually a channel on a channel. So earlier I talked about channels as first class values, right? So in Go we can actually pass a channel on a channel. So here processing queue channel is a channel which is actually a channel on a channel to which we actually push each of the channel to. And what happens? So how are we guaranteeing the ordering here? So let's see. We are in the fan-in part. Earlier we have in the fan part different Go routines receiving from each of the individual channel of the fan-out pattern. But here what we are actually doing is we are actually listening to a processing queue channel to which a channel was actually placed. So I'll make it clear. So let's say, so in this scenario, let's say we have actually finished Go. Let's say the ordering is 1, 2, 3, 4, and let's say the Go routine 2 has finished executing. So if Go routine 2 has finished executing, it will place the result onto this particular channel, right? The result is placed onto the second channel. But in the receiver side, what are we doing? We are actually receiving it from this processing queue channel. But in the processing queue channel, it will process the first channel first. So it will be waiting for result from the first channel. Then only it will execute the second channel. Even though result is placed onto the second channel, we won't be executing, the values won't be received in the aggregator side. So it will actually wait for the first channel to receive the input, and thus we can actually guarantee ordering as well as the concurrent process. We could actually concurrently process it, and the result is there. We could actually guarantee ordering using this buffer channel or queue channel. So this is an interesting pattern to note. This is the pseudocode for that. It's the same code as earlier. We listen from the events. The only thing is that we'll do this before creating the Go routine. That is, we'll pass that channel to which the Go routine will place the output to a different channel. So this is a channel on a channel, and this is the channel in which the fan-in will actually listen to so that it could guarantee the ordering. This pattern is actually used in one of the modules in Kubernetes. Kubernetes is an entire Golang ecosystem. So I'll just simply explain it. Let's say there are like multiple events, like pod created, pod deleted, right? So we receive like multiple events. So we want to receive the event, process it, and finally get after processing, we want to receive the events in the same order. We don't want to receive the deleted event first followed by created event, right? So that we'll lose the consistency over there. So let's see. So we have created the same pattern. We are creating a channel on a channel, and first, so let's see. Let's say the pod deleted event has processed first. It'll push it onto this channel, the pod deleted channel. But this won't be consumed. Why? We have a pod created channel. So the the fan-in part will actually consume from the first channel. It'll be a blocking operation there. Yeah, so this is the same pattern that we could actually use to guarantee the ordering. Now, wrapping up. So always try to embrace Go's concurrency model. So Go's concurrency model, try to always optimize for correctness first whenever you are designing concurrent applications, and also try to always share by communicating, and don't communicate by sharing memory. So that is the simple principle but very effective one whenever you are writing concurrent programs in Go. Think always in terms of patterns. Try to reuse existing solutions for existing problems. And keep it practical. Always try to focus on real-world problems and trade-offs whenever you are actually choosing different concurrency strategies that you are actually going to implement. So, yeah, that's it. Thank you.